Another important algebraic structure is the ring. So the ring consists of two operations. So we have the set R, the operation that we're going to call addition, and then the operation that we're going to call multiplication. So this is a ring if the following criteria are fulfilled. So for the addition operation, it must be commutative, it must be associative, we must have the zero element, and we must have the negative of A. For the multiplication operation, it must also be associative, it must have the identity element that we're going to write as a 1, and it needs to be distributive. So distributive laws must hold, and these laws will combine the addition and multiplication operations. So A times B plus C will be A times B plus A times C, and B plus C times A will be B times A plus C times A. There are a few things that we can note here. First of all, we have two operations instead of one, as we had in the case of a group. And second, if we look at the addition operation, then these four will correspond to the definition that we had for a commutative group. So we can say that a ring is a commutative group under the addition operation. It is important here that we remember that the operations addition and multiplications doesn't necessarily have to be the addition and multiplication that we are used to when we are adding and multiplying numbers. This could be defined differently. It is just called addition and multiplication in the ring. It is also worthwhile to emphasize that this is the definition of a ring, so there is no need to prove anything of this, because this is by definition, it will always hold. The cancellation law, on the other hand, is not by definition, but this is instead a theorem. So we have let R plus and multiplication be a ring, and the elements A, B, C belongs to the set of the real numbers here. Then the cancellation law is fulfilled, that is, if A plus B equals A plus C, then we have B equals C. And when we want to prove this, we use the definition. So what we want to show using our definition is that if A plus B equals A plus C, then we have B equals C. So let us write B. We can rewrite B as B equals B plus 0. And when we're doing this, we're using the fact that we have the 0 element. Now B plus 0 can be rewritten as B plus A plus minus A, because we know that the negative of A exists and A plus minus A equals 0. Because of the associative law here, we can rewrite this as B plus A plus minus A. And using the commutative law, we can rewrite this as A plus B plus minus A. Now we have said that A plus B equals A plus C, so this can be rewritten as A plus C plus minus A. And again, the commutative law will allow us to rewrite this as C plus A plus minus A. And using the associative law, we will have C plus A plus minus A. And A plus negative A will be 0, so we can rewrite this as C plus 0, which will be equal to C, because again now we have used the fact that a 0 exists. So we have here shown that if A plus B equals A plus C, then B will be equal to C. Another definition is that of a commutative ring. So we have the set R and the operations addition and multiplication. This is a commutative ring if it is a ring and multiplication is commutative. So if we have A plus B equals B plus A. Remember that addition is always commutative in a ring, but multiplication is only commutative if we also have a commutative ring. So here is another theorem. So in a ring that we here call R and the operations addition and multiplication, the elements 0, 1 and the additive inverse are all unique. And again, the theorem will be proven by using our definition of the ring. Let us start by showing that the zero element is unique. So let us assume that it is not unique. So this 0 here, it is not unique. So that means that we have a plus 0 equals a, and we also have another 0 element such that a plus 0 prime, can we call it, is equal to a. And this should hold for any a in our set R. And this should also hold for any a in our set R. So since this will hold for any a in the set, let us take the first expression here and we say that this should hold for the element 0 prime. So 0 prime plus 0 is then equal to 0 prime by our definition. And for our second expression here, this should hold for the element that we call 0. So then it means that 0 plus 0 prime should be equal to 0. And this follows directly from our definition because a plus 0 equals a. And both 0 and 0 prime, we have said that these are our 0 elements. But since we also have our commutative law, we can rewrite this second one as 0 prime plus 0 equals 0. And now we can just compare these two expressions here, and it says that 0 prime plus 0 equals 0 prime and 0 prime plus 0 equals 0. So this must mean that 0 prime will be equal to 0. So this element must be unique. So now we move on to show that our 1 is unique. So this will be done similar to the case that we had for the 0. So assume now that the 1 is not unique. So it means that we can write a times 1 equals a for any a in R. And we can also write, if we have another element that is also a 1, we call this 1 prime. This will equal also a, and this will hold for any a in R. Now what we do is that we say that for the first expression, we just say that a equals 1 prime, which means that it says 1 prime times 1 equals 1 prime. And for the second expression, we just say that a equals 1. So then it says that 1 times 1 prime equals 1. And since our identity element here will commute, we can write this last expression as 1 prime times 1 equals 1. And if we now compare these two expressions, it is clear that 1 prime equals 1. So the identity element must be unique. And finally we show that the negative a, or the additive inverse, is also unique. And again we will show this by assuming that it is not unique. So if it is not unique, it means that we have one additive inverse that we can call minus a, and a plus the inverse of a here will be 0. And if we have another element that also has this property, so we say that a plus, and we call this element b, this is also 0. But since we know that the 0 element is unique, we can now write this as a plus minus a will be equal to a plus b, which means that negative a will equal b. So we have shown that the additive inverse is also unique.